If you want to build a machine that can think, remember, and execute complex logic, you start with silicon and electricity. That is the baseline assumption of modern engineering. Yet, in 1928, after a fire ripped through a storage facility, workers brought a charred pile of brass gears to the Franklin Institute in Philadelphia. The artifact came with no manual and no manufacturer's stamp. Looking at the blackened, soot-covered springs, the initial observers classified the wreckage as a ruined mechanical toy. We often look back at the Victorian era and assume their engineering was rudimentary. That assumption creates a blind spot. It stops us from looking past the brass to see the complex hardware architecture underneath. Labeling this machine a toy was a mistake. When engineers finally cleaned the gears and investigated the core mechanism, they uncovered a piece of technology that forces us to rethink the timeline of computing. The restoration team carefully realigned the brass components and inserted a heavy Victorian key into the main socket. As they wound the heavy mainspring, the tension released, the brass gears meshed, and the machine woke up. It immediately executed a highly specific sequence of motions. The mechanical arm dipped a pen into an inkwell, paused to shake off the excess drop, and smoothly drafted an intricate landscape of a Chinese temple. You can see the physical artifact right here, sitting at its writing desk. When the automaton finished the landscape, it didn't stop. It moved to the border of the paper and signed the name of its creator, written by the automaton of Maillardet. A machine built in the early 1800s successfully retained its own origin data and reproduced it flawlessly. It achieved autonomous memory nearly a century and a half before the microchip. To understand how this is possible, we have to strip away the porcelain skin and the silk clothing to expose the raw mechanics driving the hand. Henri Maillardet proved that memory is not inherently electronic. It is a physical, deterministic state that can be built entirely out of metal. We are diving into the internal hardware architecture of the Maillardet Automaton. This mechanism operates as a physical computer. The data isn't stored in code, it is stored in cams. In the 19th century, this was the equivalent of read-only memory. Look closely at how these disks are shaped. They are not perfect circles. The data exists in the jagged, irregular radii of the brass. Every peak and valley on the edge represents a specific command, functioning much like binary data. Historians have calculated the mechanical memory of this specific cam cluster. It holds approximately 300 kilobits of data, enough capacity to perfectly execute 4 intricate drawings and 3 distinct poems. Programming in brass is completely unforgiving. If an engineer files down a cam edge by an extra fraction of a millimeter, the friction changes, the pen misses the paper, and the entire dataset is corrupted. Long before silicon wafers were conceptualized, engineers achieved massive data density and reliable storage using the pure physics of moving metal. Converting the data on a spinning disk into the fluid motion of a human hand requires a triple-axis kinematic chain. As you can see in this schematic, 3 distinct steel feelers track the edges of 3 separate cams. One feeler controls the horizontal movement, the second handles the vertical movement. The third determines exactly how much pressure the pen applies to the paper. If you operate a modern 3D printer or a CNC machine, you rely on this exact same logic. The physical medium has changed, but the 3-axis synchronization is identical. The Maillardet Automaton had a fixed memory, but this image shows the jaquet-droz writer, built around the same era. It utilized an interchangeable letter wheel architecture, allowing the user to swap characters and physically program the machine to write custom sentences. Then there is the silver swan, seen here on display. To simulate the biological fluidity of a bird preening its feathers, engineers synchronized 3 entirely separate clockwork motors. The late 1700s and early 1800s operated as a sort of mechanical Silicon Valley. The artisans of this era successfully mastered the fundamental rules of robotics. If engineers possessed this level of robotic precision 2 centuries ago, we have to ask why it seemingly vanished from public view during the Industrial Revolution. They hit a scalability wall. Building a 6,000-part mechanical brain required months of artisanal craftsmanship. That deliberate pace simply could not compete with the heavy, rapid mass production demands of the steam era. But the underlying logic survived. Look at the internal mechanism of this jacquard loom. The mechanical memory of the cams was flattened out into punched cards, allowing factories to automate highly complex weaving patterns. By examining this early punch card machine, you can trace a direct lineage from the Jacquard loom straight to the first IBM mechanical computers. The physical logic of the automaton is the true ancestor of modern code. Here is a modern Boston Dynamics robot demonstrating precise object manipulation. When you strip away the lithium batteries and the digital sensors, the kinematic chain moving that arm is built on the exact same foundation as the Maillardet machine. We tend to look at humanoid robots as an entirely modern invention. In reality, we are simply witnessing the perfection of an architecture that was forged in brass over 150 years ago.